This video will just walk us through this program that uses logistic regression to do binary classification, in other words, classification between two groups using the MNIST database. Okay, so let's just clear all, load the database, and then now this program is just going to decide or construct a classifier to decide whether a particular number is a 5 or not a 5. Okay, so that's why it's a binary classification. It's just dividing the whole data set into two pieces, 5s and not 5s. And by changing this number to 6 or 7, you can design classifiers that will distinguish between 6s and not 6s, or 7s and not 7s, and so on. Okay. Okay, so that's it. And then here there's a loop here which I've commented out where you can just run the whole loop and design 10 different classifiers that will tell you, okay, whether the number is a 0 or not a 0, 1 or not a 1, 2 or not a 2, etc. Okay. Okay, so here we have we're just loading the training set, the testing, training X, training Y, the inputs and the outputs, and just for simplicity of demonstration here, I'm using just the first 4,000 images rather than use all the 60,000 images. Okay, and the reason, as you will see, is just to make the thing run faster. You could use this whole 60,000 image data set, and that will be a bit slower, probably, I guess, 60,000 divided by 4 times. You can check how the scaling goes with the number of images. Okay, so here we're just measuring the length of the data sets. We have 60,000 training data images. We have 10,000 test images. The number of pixels in the X and Y directions for the images 28 and 28. And the dimensionality of the input data is 784, right? So recall that we had inputs, we had situations where we had 2 inputs, 3 inputs already in your homework. Here we have 784 inputs, okay? So each pixel you can think of as an input. And the output is whether the number, the whole number, is whatever the number is, okay? Okay, so while list, if you recall while list, oops, let me load this thing. So if you look at what train Y is, it's just numbers between 0 and 9. It tells us whatever the number the image corresponds to, and then we create this new output called Y list, which is whether or not a particular value of train Y is equal to this, what I call this what number, 5. Okay. So train Y will be, when it's equal to 5, Y list will be 1. When it's not equal to 5, it will be equal to 0. So what we have done is we have converted this 0 to 9 integers into 0 or 1. In other words, binary output. Okay. So if you go Y list, it's just zeros or ones. So that's going to be our Y list, and that's what we're going to use. And then the input matrix. So recall that your X matrix for this problem needs to be a column of ones, and then the columns corresponding to each input, right? Here we have 784 inputs, one corresponding to each pixel. And in fact, those 784 columns are contained in TrainX, right? TrainX has 784 columns. Okay, it already is arranged in terms of columns, and it's got 4,000 rows because that's how many data points we chose to use now here. Yeah, so when you go column of ones and train X, it already has now 785 columns, and so logistic regression problem has 785 unknowns, one unknown corresponding to the constant term, and then one unknown corresponding to each input, the coefficient of each input in the linear expression that goes in the exponential guess. Okay, so that's your X matrix, 785 columns, 4,000 rows, or 60,000 rows if you use the full data set. And then what we do is we convert X matrix into double. Okay, what does that mean? This is an integer data type. This is something that you don't usually have to do in MATLAB, but just safe to do it. Train X is in this format called uint, 8-bit integers, because they are images, as we discussed last time. But because you're multiplying, dividing with other double position floating point numbers, basically real numbers, we will convert that to double just to be safe. Okay. I say real numbers, more specifically double precision floating point numbers. Okay. Okay, so the B input is the list of coefficients. We just define it to be the list of zeros, and zeros works pretty well as an initial seed for this optimization problem, right? Okay, and then we have options, which just sets what the optimization options are. And these are all exactly the same as before. So once you've defined X matrix, everything else is exactly the same as before, whether it's a 2-input problem, 3-input problem, even 1-input problem. Exactly, everything follows exactly the same way. Okay. In FMIN-UNC, it's important to note that we give it additional inputs, right? So just to recall, we have 3 inputs that this function takes that we are trying to minimize. This is the unknown input. These two are known inputs. Okay. And when you call fmin-unc with this function, the initial guess for the unknown input options, and then come the 2 known inputs, which are X matrix and Y list, that that this function needs to evaluate the output. Okay, so any known inputs that this function takes, how many ever they are, should come after the options variable. That's the syntax of fmin-unc. And of course, you should make sure that the order in which this comes is exactly the same as the order in which that is specified here. So we can run that, and then let's see what that happens. What happens when we run that? So let me run that from the beginning just to be safe. Because it's a bigger optimization problem with many more data points, and each data is much more complicated. Now you will see that the optimization takes a while. F of x is the function, the logistic loss function, which is being minimized, and the function itself is being called tens of thousands of times. It's that function has been evaluated 23,000 times now, 25,000 times, right? So the optimizer is calling that function over and over again with different values of B input to figure out what is the best value of B input that sort of minimizes the function, right? So we will talk about optimization algorithms in some detail in a couple of weeks. But here we're just using an optimization algorithm to find B input. Hopefully it should be done soon. Okay, it said solver stopped prematurely because the maximum number of function evaluations was reached, it should be fine. So if you get a result like this, you can increase the number of function evaluations to something larger. Here it's well 50,000, I suppose. We can make it 100,000. Will take twice as long. I'm not going to rerun it in this video, but you can try to run it again later on to see if it converges to something better. Okay, so I'll let you do that. Well, why not? Let's just run this thing. So this will now go beyond 50,000. So as the thing is running, let me just talk through what's going on in the program. Let me comment this out. It's not super important. Okay, so once you've gotten B result or B input, the correct value of B input, okay, the program is going to complete the optimization and sort of run these cells as well. So I'll control C out and then run these step by step. Nevertheless, okay, so what does this piece do? This piece actually tests the classifier now. Okay, how does it test the classifier? It's going to use the test data set, okay, and it's going to randomly sample from the test data set just for fun, I guess, and then first display it, okay, display it like we have done before, and then what do you do? This M is now a row vector with 784 numbers. We've just gotten B result, which is B1, B0, B1, B2, B3 till B784. Okay, so what do? We basically compute the quantity B0 plus B1 times M of 1, B2 times M of 2, B3 times M of 3, etc. Right? So M has 784 numbers, grayscale value for each of the pixels. We just go B0 plus B1 times pixel 1, B2 times pixel 2, B3 times pixel 3, etc. And then we compute a quantity, that linear quantity B0 plus B1 times pixel 1, B2 times pixel 2, etc. That's basically computed in this manner, in a sort of compressed manner, right? So it computes this quantity. Let me control C out. Okay, it still stops prematurely, but if you have more time offline, you can run it for longer to see if it does better. It seems to keep doing better, actually, although, yeah, so previously I think around 50,000, the objective function was 0.06, now it's 0.035. It's pretty small, it's pretty good right now. Okay, let's actually run this little loop to see what it does. So it's going to randomly display a figure and then use the B result that we have computed just now through the optimization, compute this quantity for that image, and then that's what we're going to call Z. And then if Z is greater than or equal to 0, it's going to say it's a 5. If Z is less than 0, it's going to say it's not a 5, right? So this is basically the classifier or the decision rule, whether this quantity is greater than 0 or less than 0. This quantity equal to 0, like B2, M2, B3, M3, etc., B784, M784, equal to 0, it would be the decision boundary. It's actually a plane in 784 dimensional space. Recall that the input dimension is 784, right? Because there are 784 numbers to the input of each data point. So it's a 784 dimensional space, and this is a plane, a flat object, a plane in 784 dimensional space. Okay, and if you're on one side of this plane, it says it's a 5. If you're on the other side of a plane, it's not a 5, right? So each data point is a point. Each image is a point in the 784 dimensional space, and if this point lies to one side of the plane, it's a 5. If the point lies on the other side of the plane, it's not a 5. Or at least that's the classifier. So let's actually see how well it works. Let me run this. Okay, it says, okay, it just plots this image, and then our classifier thinks it is not a 5, which is good. It's not a 5. It's a 6, and it says it's not a 5. It's 3, and it says it's not a 5. 6 and not a 5. 7 and not a 5. 8 and not a 5. 4 and not a 5. 4 and not a 5. Okay, looks like we're not really getting any 5s here. Let me run the thing again to see if maybe we get any 5s and sees. Let's see if it get any 5s right. Interesting. The random selection seems to not contain any 5s. Okay, there you go. There's a 5. It's actually a pretty weird looking 5, and it correctly says it's a 5. Okay, that's pretty good. Okay, again it says the number is a 5 and it's a 5. That's good. Okay, I don't know if I saw any errors that the thing made. Actually, let's maybe run it once more. Maybe it did, but again it got it right. When it's a 5, it says it's a 5 using this linear decision boundary. It's saying it's not a 5 for all the not a 5s. Pretty good. Again, it's a 5, and it says it's a 5 even though it looks pretty different. It's 25. Okay, it's a weird 4, but it says it's not a 5, certainly, which is true. Okay, so it looks to be doing pretty well, not too bad. Okay, so already you should know that, okay, here's a way we can actually, how would you quantify the performance of a classifier like this? If you have n random images, you can say how many does it get it wrong, right? And we can use the test data set because it's the data set we have not used for constructing the classifier to find the accuracy. So how do you find the accuracy? We build the X matrix again. So basically, we will compute this quantity for each data point in the test data set, and then use this rule to say whether it's a 5 or not 5, and then compare with the ground truth in the test data set. In other words, the data itself, to see if it's a 5 or not 5, and how many ever whatever fraction it gets right, that would be the accuracy, and whatever fraction it doesn't get, and that would be the error rate. Okay. Rather than do this one image by image, we can just do them all at once, where you construct this X matrix, column of ones, columns of all the inputs, and then we convert that into double precision. Then we compute Z list, which is just X matrix times B result. This basically computes this quantity for all the images in the test list all at once. Okay, so that's very fast, rather than put this in a loop, right? So in MATLAB, you always want to think whether you can put things in a loop, right? So rather than hard code something, whether you can put things in a loop, and then sometimes you can even do something that is more efficient than loops, which is matrix operations, right? Okay, so you computed Z-list. If basically Z-list is greater than 0, that's 1. That means it's a 5. If Z-list is less than 0, it's a 0. Means it's not a 5. Okay, so we're calling Y-list predicted is basically Z-list greater than or equal to 0. This will be a list of zeros and ones, and that's your prediction for what each of the images is. And of course, in the test data set, you already know what the image corresponds to. So you can say if test y equal to 5, that'll give you the actual ground truth data, right? So this is the ground truth data. That's a technical term, ground truth, or at least a somewhat technical term, what the real truth is, or at least what we think the real truth is. Okay, and then basically we need to compare these two things. Whatever fraction of indices for which these two disagree, that's your error rate. Okay, accuracy is going to be, we basically equate these two things, check where these two things are equal. Let me put this, okay, so we have y list predicted as a list of zeros and ones, and then y list test, another list of zeros and ones. And if we say y list predicted equal to y list test, we get again a list of zeros and ones, and wherever you have a zero they disagree, wherever you have a one they agree, right? So it looks like they're mostly agreeing. Occasionally there are errors, okay, occasionally there are errors, but mostly they are agreeing with each other. And then the accuracy is going to be basically the sum of all these ones divided by the total number of indices that we have at the length of this vector, right? So sum of all the ones in that equality divided by length of that vector. Okay, so that's going to be the accuracy. So let's check that. Accuracy is 96.5%, or the fraction of correct answers is 0.965, which is pretty good, looks like. Okay. Let me run this piece. It says the accuracy of this logistic regression is 96.5% in detecting whether a number is 5 or not. Is this a high percentage? For answer, see comments in the code. Okay. Here are my comments. Let me just walk you through it. 97% or 96.5% is pretty good. Maybe not perfect. It would be nice to have close to 100%. And we may be able to increase that by running it for a longer period of time, maybe with a bigger data set, etc. Or using a different method, actually. So you can check if those things improve the accuracy, running it for longer or making the data set bigger, making the training data set bigger. Because we've just used 4,000 data points, we have 60,000 data points to train this on. Okay. Okay, so is this a high percentage? Now, I'm noting here that there exists kind of a trivial classifier that already gets 90% accuracy for this particular question. Okay, what is this almost trivial and sort of wrong classifier? The trivial classifier that gets 90% is actually the following. It actually says it's not a 5, whatever number you present it with. Okay, whatever number you present it with, it doesn't even look at it and just says not a 5, not a 5, not a 5, not a 5, not a 5. Now, why is that a 90% accurate classifier? It's because 90% of your data is not a 5, so it'll get the correct answer for 90% of your data, and then for the 5%, for the 10% of the data where it is a 5, it will be wrong, but the accuracy value will be 90%, right? So 97% sounds like a high number, but it may not be that high considering that you can so easily get 90% accuracy. Okay, so that should be a note for caution, which is the way you measure accuracy and the composition of your data might sometimes lead to misleading conclusions. Okay, you have to be very careful with this. And the way here you would be careful is to actually notice that there are two kinds of errors. One is called a false positive error, another is called a false negative error. These are words that you may all be familiar with, especially in the context of, let's say, COVID-19 tests. What is false positive? Well, first you have to decide what a positive is, I guess. In this case, a positive is there being a 5, let's say. Um, False positive is when the image is actually not a 5, but the algorithm or the classifier says it's a 5. And then false negative is when the image is a 5, and then the classifier says it's not a 5, right? For this trivial classifier where it says it's a the image is not a 5 all the time, the false uh, positive rate is actually 0. It never says it's a 5, right? But the false negative rate is actually 100%, because if it's a 5, it actually says it's not a 5 100% of the time. So it's got a horrible false negative rate, right? And very often, depending on the situation, you might want both the false positive rates and the false negative rates low, but sometimes one is more important than the other, and let you think about situations in which one is more important. Okay. Um, in some applications, false positives may be more important. In some applications, false negatives may be more important. Okay. Um, how do you, yeah, so you can look through the implementation of how false positives and false negatives are computed. Basically, it first classifies the data for when the image is not a 5, right? So temp is all the indices when y-list test is equal to 0. Um, so we're just looking at all the indices where y-list. So basically, false positive rate is the error rate when the image is not a 5. False negative rate is the error rate when the image is a 5. Okay, so we basically do this comparison um, when temp is true. And here for false negative, we do this comparison when temp is not true. Okay, so this tilde, just to recall, means not not. Here we are doing when is it not equal to each other. That's the error rate, right? And then here again, we are checking when is it not equal to each other when the image is a 5 in this case. Temp is where the image is not a 5, and not temp is when the image is a 5. Okay, so that's how you compute false negative and false positive rates. So I'll let you parse through these expressions slowly and think about it. And in your homework, I would like you to compute the false positives and false negative rates as well. Okay, let me stop there. Actually, let's run this to see what your false positives and false negative rates are for this particular classifier. Okay, false positive rates, super small. So it never really says it's a 5 when it's not a 5. It looks like when it's not a 5, it basically says it's not a 5. It looks like that has that property. And then it looks like here it says it's not a 5 when it is a 5 to about 20% of the time. So 1 out of 5 times when it's a 5, it actually says it's not a 5. That's a pretty high false negative rate, right? So yeah, so I guess that's that. You can check, I'll leave this as an exercise for you to check whether increasing this 4,000 to 60,000 makes a difference in this false negative rate. Or running this optimization for longer, maybe for 1,000,000 iterations or something, makes this false negative rate lower. That may improve things. Both those things may improve things a little bit. But eventually we will also use other methods to improve this much more. Okay, this is a pretty simple method, but there are more sophisticated methods that build on this. So it turns out that something that we will learn, the so-called neural network or deep learning class of methods, could be thought of as a generalization of logistic regression in a very sort of natural way. So we will talk about that very soon.